Before you go. Wham! We all remember in the 80s where we were when Wham came out, that hit single. All right, we all remember the 80s, don't we? Yeah, good stuff, good stuff. All right, here we go. Let's go through what you're going to do with this lab. We now have our data table. The data table is very small. Very short data table here. You can see that we have some X's in our data table, and we filled in the temperature changes, and make sure we write down those masses. That's important. We are going to need those exact masses. All right, so we have our data table. That's all you need to do there. We flip, we go to the back, and we do calculations. Calculation A. Determine the molality for each of the 4 solutions. Now, the truth is, you're not going to have 4 calculations. You're going to have 2. You're going to have 2 calculations because we didn't do the boiling part. We did the freezing part. And we didn't do the boiling part because I'm not going to deal with boiling sugar and salt solutions and trying to video and trying to take temperature readings with boiling solutions. It's just not a safe thing without a lab partner. You need a lab partner for that to be safe. All right, so we just did the freezing. So there are 2 calculations for each one of these 4 calculations. All right, you'll have 2 calculations for each for a total of 8. Okay, so calculation A. Calculate the molality. Molality. I like that. Molality is moles. All right, per kilogram. And this is moles of the solute. So that's either the potassium nitrate or the dextrose. So we'll have to do this twice. Do this twice. And that is kilograms of water. Now, we all know that you and I together, lab partner, very accurately measured out 50 milliliters of water. What's a milliliter of water equal to? Very good, lab partner, a gram of water. So 50 grams of water is what we used. So put that in kilograms. Boop, boop, boop. Move it over, and you get that in kilograms on the bottom of the water that we used. This is going to be a mole calculation. You're going to do that. I'm not going to do that for you. No. At this point in chemistry, you should know how to do a mole calculation. You have grams of each one of the solutes, and that's why I said write down the exact amount that I used, because you're going to need this for the calculations. So don't just put 5, put 5.02. Don't just put 10, put 10.160. Those are your masses. So you're going to have the masses here, 1 mole, and you're going to get the grams of the potassium nitrate. And you'll do 1 for potassium nitrate, and you'll do 1 for the dextrose. Okay. You are going to need to know what the mass of the true mass is. The mass of a mole of this is. The dextrose and the potassium nitrate, so look it up. I mean, you can Google it if you want, if you think that's faster, or just look it up, or just add this all up and get a total mass for that compound, throw it underneath. Get a total mass for that, throw it underneath. Now, when you do that, when you calculate what the true mass of the potassium nitrate and the dextrose are, you're also finding the answer to calculation C. Calculation C says calculate the theoretical molecular mass of each solute. So you will have solved calculation C already by doing calculation A when you add up what the mass of this should be, and you add up all these masses and get the mass of the dextrose. Killing 2 birds with 1 stone. Nope, sorry. Any PETA people out there, you won't like that. Feeding 2 birds with 1 scone. That's pretty good. I heard that, and I like that. So that's not mine. I didn't take credit for it. Okay, but I like it. Okay, so you are doing 2 calculations actually when you do calculation A. You're also getting calculation C complete to get the total mass of each one of those. Okay, that's that. Now, calculation B is the meat and potatoes, unless you're a vegetarian. Then it would be like your seaweed or something, I don't know, of the lab. Okay, so this one is the big kahuna, calculation B. Now, calculation B, you're going to calculate what the molecular weight of these 2 compounds are using experimental data. Now, we already know by this point, if you've done calculation A, and therefore would have done calculation C at the same time, what the true masses of these compounds should be. We're going to see what the data from the lab tells us the masses would be. We're going to need our equation. This is the change in the temperature freezing equals Kf times molality. We need that. If you have watched the videos on colligative properties, and at this point you should have, otherwise you shouldn't be doing the lab yet, then I think it's calculation, hang on, stay there, don't go anywhere. Are you still there? Are you still there? Hello, McFly. Hello, McFly. Calculation 5. I was finding the problem sheet that I used to go through those calculations with colligative properties. Calculation, example problem 5. In that problem, you were using the equation here to figure out the molecular weight. Watch that video if you haven't done it. Watch it. I'm not going to do this for you. But what I will do for you, because you're my lab partner, we're buddies, we're close, we're tight. I'm going to put in, for molality, what molality can be broken down into. So molality can be broken down well, it's moles over kilograms, okay? So we can put moles over kilograms, but wait, there's more. Moles can be broken down. Moles can be broken down into mass over molecular weight. Ooh, that's how you figure out moles. You take the mass that you have and you divide by the molecular weight off the periodic table. That's how you get moles. So that's moles, and kilograms goes on the bottom. So molality breaks down to this. That's what we need to solve problem B, calculation B. You are trying to find the experimental molecular weight. We're trying to find the experimental molecular weight, which is right here. We're trying to find that. Now, I'm not going to go put stuff in here and solve this for you. You have to do it. And if you have an issue or a problem, or maybe, maybe the algebra might be a little bit iffy for you, then go back and watch the video on solving example problem number 5, because I go through this process with you, because that's what that question is about, finding that. And so go back and watch that. Okay. What you're going to have is that, and you're going to solve for that. You have this stuff. Yes, you do. The change in the freezing temperature is on the data table. We know that. For the potassium, you're going to do this twice, remember. You'll do this 2 times, once for potassium nitrate and once for the dextrose. So you'll do this calculation 2 times. All right, so the potassium nitrate went down. Its change in temperature was like 3 point something. I don't remember exactly what it was. It was 3 point something. The dextrose went down 1.3 degrees. I don't know. I remember that one, but I don't remember the other one. Okay, so you're going to use that change in temperature here of the potassium nitrate to 3 point something. The Kf is a value which is a standard value. Now, I've used it in many videos, so go back and watch it. Or if not, just look it up on your own. I'm not going to do it for you, lab partner. You're going to do something here. So get the Kf for water. The mass, if I'm using potassium nitrate, is the 5.02. If I'm using the dextrose, that mass would be 10.160. That's unknown. You're trying to find this. And the kilograms of water, which we would have already used in calculation A, right? We know the kilograms now, how much water we use. We took the 50 milliliters equal 50 grams, converted it to kilograms. That goes on the bottom. All right, then we do some cross-multiplying, dividing, and solving for molecular weight. Do that for the potassium nitrate and here. Now, No, that's not what I was going to go about. Not the coffee. This is important. Potassium nitrate is a salt. It dissolves. It breaks down. It breaks down into potassium and nitrate. Ooh, it breaks down into those parts. 2 parts, people. What does that mean? Well, if you watch the video on the Van Hoff factor, then you know exactly what I'm talking about now, don't you? Yes, you do. If you don't know what I'm talking about, then you need to go watch that video. Yes, you do. This has twice the effect, which makes sense if you think about the freezing point depression for the two. The freezing point depression for the potassium nitrate was much lower. Okay, it was much more effective. It was negative 3 point something as opposed to the sugar, which is only like negative 1.3. So why? Because this has two parts. That Van Hoff factor is a multiplier. 2 parts means I have to multiply this K value by 2 for the potassium nitrate. If you don't do that, you're going to be off by you'll be off by twice as much. So make sure that when solving this MW, the molecular weight or molecular mass, it's the same thing. Make sure you put a 2 in front of that KF. When you solve for the dextrose, do not put the 2 in front of the KF. Leave it alone. This doesn't break down into anything. Okay, so it's a molecular compound. It's not a salt. It's a sugar. So it just stays together. So there is no multiplier for this one. All right? Okay, remember that when you do calculations. No multiplier, potassium nitrate, multiplier. Do those calculations, come out with some values. Hopefully, we get close, somewhat close. This is like very difficult, the most difficult lab to do of the entire course. It's the most difficult one to do and come out with decent data. I always tell students doing this, I say, if you can get under 40%, that's not bad, accept that, because you've done all right, because it's a difficult one to do. The thermometers can be an issue. This thermometer was not an issue. It was actually did show the freezing point of ice water bath is 0. I did that off camera. I didn't even mention it before. I just forgot I did that. But I was calibrating to see where our freezing point would be with our thermometer, and sometimes students forget to do that. And so your thermometer might say -1 is the freezing point, which skews all your data. But ours isn't. It was a 0, so that was good. But there are multiple things that can really influence the outcome. And if we can get under 20%, we're doing well. We're doing really well. That's actually really good. So let's see what we get. And that's the last thing you need to do. Calculation D, percent error. So do your percent error. If you remember, your percent error is equal to true minus experimental divided by true. The true value is what you used in calculation A and what you wrote down in calculation C. That's the mass of the dextrose and the mass of the potassium nitrate as determined by adding up all their masses off the periodic table. That's the true value. Your experimental value is what you just would have found in calculation C. Put that in here, subtract them, take an absolute value, so no negatives, and fingers crossed, we came up with negative or less than 20%. We did a good job. All right, one last thing, then make sure you do the, so make sure you show 8 calculations, 4 for each sugar and salt, and then do your questions. A lot of these questions are dealing with salts dissolved in solution, determining what the freezing point and boiling point changes would be. Remember the Van Hoff factor. You got to remember that. If it's something like potassium nitrate, okay, you'd have to multiply the K value by 2. All right, okay, so remember that. Look at your salt, see how many parts it breaks down into. Use that as your Van Hoff multiplier. All right, I think that wraps it up. So good job, lab partner. Hope you did okay. All right, I hope you did all right. Talk to you soon.